Hi everyone, I'm Mr. Peck here. Welcome back to the channel. Today I'm going to start a new chapter called The Rotation of Rigid Body. In this chapter, you are going to learn 4 subtopics. The first one is called the Rotational Kinematics. Okay, I'm sure you learned about this chapter before, but in terms of linear motion. Okay, so in linear motion, you learn about displacement, velocity, acceleration, the 4 kinematics equation, v equal to u plus at, s equal to u, ut plus half at square. Okay, and all those. Now we just want to translate to the terms in rotational motion. Okay. Then the second subtopic, we're going to learn about equilibrium of rigid body. Also, we have learned in previous chapter forces. We learned about equilibrium. When reach equilibrium, the total force is 0. We have also the terms in rotational motion. Okay. Then it's about rotational dynamics. Rotational dynamics is about Newton's second law. Total F equal to ma. We also have terms in rotational motion. And conservation of angular momentum. This is the last subtopic. You learn about conservation of momentum. m1u1 plus m2u2 equal to m1v1 plus m2v2. Now, we are going to translate that all to terms in rotational motion. Okay? Now, let us start with the first subtopic, rotational kinematics. Okay? Rotational kinematics. So, before, in linear motion, you learn about displacement. Okay? Displacement. So, in rotational motion, we also have angular displacement. Angular displacement. So the difference is displacement is in terms of length. So the unit is meter. But rotational motion, the angular displacement is in terms of angles. That's why it uses radian. Okay? And then in linear motion, we have velocity. Rotational motion, we have angular velocity. Linear motion, we have acceleration. Rotational motion, we have angular acceleration. So you see the unit, they are similar. This one is meter, velocity is meter per second, acceleration is meter per second square. So in rotational motion, just change to angles. That's why it's radian, radian per second square. Okay? And then you see, in between them, they have similar formula. Similar formula. S is equal to r theta. Okay, V equal to R omega, A equal to R alpha. You see these three, they are in similar format. Okay, we are going to use this formula. And of course, acceleration in our terms now, we call tangential acceleration. I will talk more about tangential acceleration later on. Okay, just bear with me. So in linear motion, we learn about the 4 kinematic equations, namely v equal to u plus at, s equal to half u plus vt, s equal to ut plus half at square, v square equal to u square plus 2as. Now we translate that into terms in rotational motion. V is omega, a is alpha, s is theta. And you see, when they change to the terms in rotational motion, they look similar, isn't it? V equal to u plus at become omega equal to omega naught. Omega naught means the initial velocity. Okay, plus alpha t. A is alpha. And then s is theta. So that's why it becomes theta equal to half omega naught plus omega t. S equal to ut plus half at square. So it's become s become theta, u become omega naught, and a become alpha. Become theta equal to omega naught t plus half alpha t square. And then we have v square equal to u square plus 2as. So v become omega, u become omega naught, a become alpha, s become theta. See? Omega square equal to omega naught square plus 2 alpha theta. They are similar. Okay? So this chapter, rotation of rigid body, is not difficult because we learned the concept before in the previous chapter. We just translate them into the terms in rotational motion. And then this is also very important. N is called the number of revolutions that has been traveled. So N is equal to total angular displacement divided by 2 pi, the angles for one revolution. So the total angular displacement divided by the angles for one revolution, which is 2 pi, then you will get N, the number of revolutions. Okay, this will be used in the further calculation. And then we also have this called RPM and RPS. What are they? RPM is revolution per minute. RPS is revolution per second. Okay, so these are the units for omega. But for omega, we normally use radian per second. Omega. So you need to change the RPM and RPS to radian per second. So how to change? For revolution per minute, you just multiply 2 pi over 60. You will get radian per second. For revolution per second, you just multiply 2 pi. You get radian per second. Okay, that's about omega. And then omega also have another two formula. Omega also equal to 2 pi f or 2 pi over period. Why? Because the frequency is actually 1 over period. You just substitute into it, you get 2 pi over period, right? Okay, and then for this one, this is also a very important concept. Assume that this circle is rotating anti-clockwise. It is rotating anti-clockwise. Now you have object, this is the center. This is object 1, which is nearer to the center, and object 2 at the rim of the circle, which is very far away from center. Okay, so R1, this is distance of object 1 to the center, and R2 is the distance of object 2 to the center. V1 is the speed, the linear speed or linear velocity of object 1, and V2 is the linear velocity of object 2. Omega is the angular velocity for both objects. Now, we learned about this formula, V equal to R omega. So we can apply here. So for object 1, it is V1 equal to R1 times omega. V2 is equal to R2 multiply omega. Okay. So as you see, for both objects, this is very important. For both objects, they have same omega. What is omega? Angular velocity. For both objects, they share the same angular velocity. They have the same angular velocity, for both objects. But the linear velocity V2 is faster than V1. V2 is bigger than V1. Why? Because the radius 2 is bigger than radius 1. Radius 2 is bigger than radius 1. So I can say that object 1 travels slower, but object 2 have to travel faster. Okay? But for both objects, they have the same angular velocity. Both of them, we can say that both of them complete the circle at the same time. Or we can say they have the same period. When omega is the same, when they have equal omega, of course they have equal period. And also they have equal frequency. Okay? It's same omega, same period, same frequency. So both objects, they have same omega, same period, and same frequency. But of course the speed, object 2, in order to complete the circle at the same time with object 1, object 2 have to travel faster to catch up, isn't it? Because it is the radius is bigger than radius 1. Alright? Okay, enough of that. Now, for these two, we have tangential acceleration. We learn in this chapter, we're going to learn tangential acceleration and angular acceleration. These are the two new things. Tangential acceleration, symbol is AT. Angular acceleration is alpha. And their formula is AT equal to R alpha. AT is tangential acceleration. Alpha is angular acceleration. Okay, and these are the unit. Tangential acceleration is meter per second square. Alpha is radian per second square. So tangential acceleration is in terms of meter. Alpha is in terms of radian. Okay. Now, in previous chapter, circular motion, we learned about centripetal acceleration. AC. The formula is V square over R, or R omega square, or V omega. You see, centripetal acceleration, AC, is different from AT. The formula is different. Sometimes we also call, this centripetal acceleration as radial acceleration. The symbol we put as symbol we put as symbol is AR, radial acceleration. Now, what's the difference between centripetal acceleration and tangential acceleration? Well, if you see, let's look at the direction first of all. Tangential acceleration is tangent to the circle. Tangent, just touching the circumference. Tangential acceleration. It is parallel to the velocity. Tangential acceleration is parallel to velocity, and it is tangent to the circle. But centripetal acceleration is towards the center of circle. It is perpendicular to the velocity. We also can say centripetal acceleration as radial acceleration. Why we call radial acceleration? Because it is on the radius. Centripetal acceleration is also radial acceleration because it is on the radius towards the center of circle, perpendicular velocity. This one, yeah, perpendicular to the velocity and towards the center of circle. Do they have the similar function? Do they have the same function? First of all, their equations are different. So their direction also different. So the function also different. Tangential acceleration, because it is parallel to the velocity, that's why it can change the magnitude of velocity. What does it mean? It means that the velocity becomes faster or becomes slower. If acceleration becomes, the object will spin faster and faster, the magnitude of the speed becomes faster and faster. If deceleration, the velocity becomes slower and slower. It spins slower and slower. Change the magnitude of velocity. This is the tangential acceleration and also the angular acceleration. AC, centripetal acceleration, it is perpendicular to the velocity, so it does not change the magnitude of velocity, but it changes the direction of velocity. It makes the object, it changes the direction of velocity so that it does not move in a straight line, but it moves in a circular motion. The centripetal acceleration directed to the center continuously change the direction of velocity so that it bend, and as a whole, the object will move in a circle. So it changes the centripetal acceleration, it changes the direction of velocity so that the object will move in the circular motion continuously. Alright? So that's it. So another thing is, let's go back to the unit. Tangential acceleration, the unit is meter per second square. Same as centripetal acceleration, also meter per second square. only the angular acceleration is radian per second square because it is measured in terms of angles. All right? So that's it about the kinematics for rotational motion. All right? I'm sure you learned something. Okay? So this is the first subtopic. Now we go on to the second subtopic called the, what is it? Yes, equilibrium of rigid body. Okay, equilibrium of a uniform rigid body. In linear motion, we learn about force. Force will make something move to the left, to the right, upward, downward. Okay, it will make something move. But in rotational motion, we have torque. Torque, you see, torque. Torque will make something rotate. That's it. It will make something rotate for rotational motion. The unit for force is Newton. Torque is Newton meter. Why torque is Newton meter? Because torque is equal to R cross F. Torque is a cross product. When cross product, we use sine theta. Sine theta. Why is it sine theta? So many questions. Okay, I will explain one by one. First of all, okay, we have R. What is R and what is F? Let's look at this diagram. As I said, torque will make something rotate. Yeah, torque will make something rotate. So to make something rotate, we need the distance R and also we need a force. So how to get the distance R? See, I have a rod. And this rod is fixed as this point, which is we call axis of rotation. Axis of rotation or pivot. That means this object, the entire rod will move except this point, which is the pivot. Sometimes we call it hinge. Hinge. Yeah, sometimes we call it the hinge. Okay. Now, so this point will not move. Now, I exert a force with an angle theta over here at the other end. I push it. I push with force F. This force F is a distance R away from the axis of rotation. Some distance away. Distance R. Okay? Now, this force F can be resolved into two components. Okay? Because we have angle theta. So, adjacent to angle theta, we have F cos theta. And then, opposite to the angle theta, we have F sin theta. So, F cos theta is parallel to R. F sin theta is perpendicular to R. You see? Which force, I ask again, which force will make this object rotate? Is it F cos theta or is it F sin theta? Will F cos theta make the things to rotate? You see, I fix it over here. I push it this way. I push it this way. Will this thing rotate? Will this thing rotate? No, it won't rotate. But if I push it this way, when the force is perpendicular, you see, when the force is parallel to the R, is it rotate? No, no rotational motion. But when the force is perpendicular to the R, will that thing rotate? Yes, it rotates. You see? When the force is perpendicular to the R, it rotates. Okay? So, it is the F sin theta which rotate the object. Rotate the object. The F cos theta has no use. I can cancel that out. Yeah? This F cos theta has no function in rotational motion. Only the F sin theta will rotate the object. That's why for cross product of torque, we use F sin theta, the perpendicular component of force, to multiply with the R, to multiply with the distance of force from the pivot. That is R. What is R? R is the distance between force and the axis of rotation. And that is R. So only the F sin theta will rotate the object. So that's why we use F sin theta to multiply R. then we have Fr sine theta. This R go in between, we have Fr sine theta. That's why cross product for torque, cross product use sine theta. Why sine theta? Because it uses a perpendicular component. Okay, that's how simple. Once it rotates, the object will move upwards. You see, it rotates this way. This axis of rotation never move. All the other parts move upward, except this axis of rotation. Okay, that's how we calculate torque. Simple, isn't it? So torque, as I said, force makes something move, torque makes something rotate. You see, this rod rotate. Torque will make something rotate. And how to calculate torque? Just use the perpendicular force multiplied by the distance, R. Okay, enough for that. Now, Newton's first law. Before that, we learned about point mass. We just consider all masses as just one point. Yeah, all the mass of the object concentrate at the center, and we see the object not as a big object, but just a point mass, or we can say it is just a particle. Okay, particle. So for equilibrium of point mass is very simple. We just consider total force equal to 0. This is Newton's first law. Total force equal to 0. And we just think about x and y component. Total Fx equal to 0. Total Fy equal to 0. Okay? Very simple. So we just consider force to the right as positive, force to the left as negative, force upward positive, force downward negative. This positive negative just to show the direction. But for equilibrium of rigid body, it has two conditions. The first one, of course, same as the before, total force must be equal to 0. Total force Fx, total Fx equal to 0, total Fy equal to 0. Also, we use this direction, going right positive, going to left negative, going upward positive, going downward negative. The horizontal is the x, the vertical is the y. Now, for rigid body, we're not just talking about the object moving to the left or right, upward, downward. We also visualize the object, the rigid body, can rotate. Rotate clockwise or rotate anti-clockwise. So, for a rigid body to be in equilibrium, the total torque must also equal to 0. Total torque equal to 0. That means the torque making the object turn anti-clockwise must balance out by the torque that rotate the object clockwise. Both of these must be equal. So that total torque equal to 0. Okay, we will later we will discuss question on this to understand more. So we also for this one, we think that the torque that make the object turn anti-clockwise as positive. Okay, but if the torque make the object turn clockwise, negative. So anti-clockwise, AC is anti-clockwise, CC is counterclockwise. Counterclockwise, same meaning. Anti-clockwise, counterclockwise, same meaning. So anti-clockwise, counterclockwise, they are positive. Clockwise, it is negative. Okay, this is just the positive negative just to show the direction. Now, this is about equilibrium of rigid body. We will discuss more questions on this. Next is rotational dynamics. Rotational dynamics. Rotational dynamics is about Newton's second law. Just now, equilibrium is about Newton's first law. Total force equal to 0. Total torque equal to 0. But in rotational dynamics, it's about Newton's second law. Total F equal to ma. Remember? Okay, now, first of all, you must know, linear motion, we learn about mass, isn't it? We learn about mass. In rotational motion, we learn about moment of inertia. Mass is kilogram. Moment of inertia is kilogram meter square. Why the unit is kilogram meter square? Because moment of inertia is the summation of mr square. M is kilogram, r is meter. So mr square is kilogram meter square. This is the moment inertia. And also we have several shapes. We have solid disc or solid cylinder. We have hollow disc, hollow cylinder. We also have their respective formula, but this formula no need to memorize because they will be given in the exam, in the questions, right? So and also we have several other forms like sphere, rod. Okay, those formula will be given. But the most common formula that are used is the solid disc and hollow disc, yeah, or cylinder. The solid disc formula is half mr square. Hollow cylinder is mr square. These are very commonly used formula. Okay, hollow disc is mr square. Solid disc is half mr square. These formulas are for the moment of inertia for these shapes. Okay. Now, Newton's second law. Newton's second law, in linear motion, you learn about total F equal to ma. But rotational motion, we learn about total torque equal to I alpha. Still remember, force is equivalent to torque. Mass is equivalent to I. You see? Mass is moment of inertia, I. And acceleration is equivalent to angular acceleration. A or equivalent to alpha. So this is the Newton's second law in terms of rotational motion. This is Newton's second law in terms of linear motion. Okay? So similar. You learned that before, isn't it? So the rules also same. About the positive negative. Remember? Follow in the linear motion, we say that follow acceleration, all the forces that follow acceleration will be considered positive. All the forces that are opposite to the acceleration considered to be negative. Because why? Because we think that the force that follow the acceleration are the bigger force. Force that opposite the acceleration are the smaller force. That's why they're negative. So this is like big force minus the small force. Yeah. I hope you understand what I mean. Yeah. And then for the rotational motion, same. Since acceleration now is alpha and force is torque, so the torque that follow the angular acceleration alpha, torque that follow the alpha will be positive. Torque that they are opposite to alpha will be negative. The torque that follow the alpha is actually the bigger torque. Torque that are opposite the alpha, they are smaller torque. It's like the big torque minus a small torque. Okay? So same rules. I will use an example to discuss this later. Then is another very important thing. This A can be changed to alpha. A equal to R alpha. And this alpha also can be changed back to the A. Alpha, this formula comes from A equal to R alpha. So R just go below. So that's why alpha equal to A over R. If the question asks for us to find, let's find A. If the question wants to find A, then this alpha you just change to A over R. If the question asks for alpha, so this A you just change to alpha, use A equal to R alpha. You don't understand now, never mind. I will use an example to explain later. Okay, so you must look for the upcoming videos about in this chapter 8. Okay, I will solve several problems to discuss in details. Thank you for your time. Yeah, and now the lastly is about conservation of angular momentum. Conservation of angular momentum. In linear motion, we learn about momentum. Momentum symbol is P. P is mass times velocity. Yeah, momentum is mass times velocity. So in rotational motion, we have angular momentum. Angular momentum is L. The symbol is L. Okay, and mass is moment of inertia. velocity is angular velocity. So angular momentum is I omega. P equal to mv. So L equal to I omega. Okay? They are equivalent. So the unit for momentum is kilogram meters per second. For angular momentum, it is kilogram meter square per second. Kilogram meter square per second. Then also about the kinetic energy, we have translational kinetic energy in linear motion, half mv square. So m is like moment inertia, v is like omega. So rotational, we also have rotational kinetic energy. When something rotates, it has rotational kinetic energy. When something travels to the left or right, upward, downward, that is translational kinetic energy, half mv square. So both rotational kinetic energy is half I omega square. The unit is the same because both of them are energy. Both of them are energy, so they use joule. Okay? Lastly, it's about the conservation of angular momentum. Yeah? So before we learned about conservation of linear momentum, total initial momentum equal to total final momentum. M1U1 plus M2U2 equal to M1V1 plus M2V2. So in rotational motion, we have total Li equal total initial angular momentum equal to total final angular momentum. I omega initial equal to I omega final. Okay. Also, I will have one example to discuss about this. So you see, all of these we have learned before. All these terms we have learned before. Okay. The conservation of momentum, Newton's second law. All right, Newton's second law, total F equal to ma, and equilibrium, total F equal to 0. Yeah, and also the kinematics, or the 4 kinematic equation V equal to U plus AT, all these things. Yeah, we already learned this before. Now we just translate them all into terms in rotational motion. It's not difficult, all right? So I hope that you stay tuned for the upcoming videos on more details. The problem solving, yeah, will be discussed in details, and I hope you enjoy it. Thank you for your time. Bye bye.